All right. I talked about this before. End of last class, we finished off talking about this. We got this model of the Earth that's supported by these two cords, wires. They're calling them wires. These two wires here, and it says determine the range. Well, it's revolving at a constant speed. Determine the range of the allowable values of V if both wires are to remain taut. So V being velocity. If the tension in either wire is not to exceed 116 newtons. All right, so let's work this out. It's a fun little problem. So this is an interesting problem because it doesn't. You don't actually have a. It's not like you're solving for one single answer. You're solving for what's a range of velocities that you can tolerate. So we have the first thing I want to do is draw out a free body diagram of this thing. But notice here, there's no theta component of acceleration. Right, so this is a constant velocity. So in terms of a theta component, there's no theta component. There is just and we'll see in a minute, the normal component of acceleration. So what I want to draw here, if I can do it, I need to get a stack of a couple coins here to make better circles. Let me draw this. All right, let's put in some tensions. Oops. So I have 40 degrees and 15 degrees. And notice this is 15 degrees from the center. I'll draw a center in here. Red. So I'm going to call this tension. I'll call it tension CA. And this is tension CB. So from point C to point B, point C to point A, let's try to put some other forces in here. The other force that's acting on this thing is the weight, right? It's a 5 kilogram model. And I'm going to draw my axes. I'll just draw my axes up here. X and Y direction. What am I missing? I put some angles in. Oh, I suppose I did need some kind of. So this in here is 15 degrees. All right, be careful your, right, it's 15 degrees here, but it's running through the center of the globe is a vertical line, so it's alternate. What is it called? Between two parallel lines, or whatever that rule is called. I never remember the names of these things. 40 degrees. All right. So this is our force diagram. This is our free body diagram of the globe, or the model, whatever it is. Now we have to set that equal to the kinetic diagram. And this is where I want you to notice there's no theta component of acceleration, right? The only component of acceleration is inward. So this is mass times the normal acceleration. All right. So also be aware, right? W is what, 5 kilograms times 9.81 meters per second squared. So W is 49.05 newtons. I always like to carry a few extra digits during the calculation and round at the end. Let's see, what else do we need to know? All right, so the two equations we really need to look at initially are, if we look at this force balance or force to kinetic diagram, right? We've got two things going on. We've got some of the forces, the normal components equal mass times acceleration normal. And I just want to write this out, so don't worry about this yet. Some of the forces in the tangential direction are MA tangential. Now, I want you to notice here, right? This M, the normal component of acceleration in these coordinates is v squared over rho, right? The tangential component right? We know the velocity is constant. We're told that the velocity is constant, or constant speed. Now, this goes to 0, this term here. We're still left with the sum of the forces and tangent now equals 0, right? There's no acceleration in that dimension. All right, so we're going to look at x and y coordinates just because it's, you know, you can visualize that a little and break these down. And we're not interested, again, in and out of the page. That's not concerning to us. So let's look at the sum of the forces in y. So I'm going to just break these down. We're going to have components, right, of everything going on here. Oops. Oh. Sum of the forces in y. All right. So the sum of the forces in y, notice there's no y component of acceleration. So this is just going to equal 0, right? And let me just also put x. X up here is also the, well, it's negative normal. We'll get to that in a minute. So what do I have? I've got the tension of CA is pointing upward, and the y component is going to be cosine 40. Then I've got TCB pointing downward, right? So it's a negative. And I've got TCB. In this case, oh, I didn't label the, well, I did, it's 15 degrees. That looks like 150, but that's not. It's cosine 15. Don't forget the W. So we have an equation here, TCA equals W plus TCB cosine 15 over cosine 40. The next thing I'm going to do here, well, you know what? I'm going to expand this out. If you put the numbers into this, which it looks like that's what I did. Where's on my finger? You wind up with TCA equals 1.26093 TCB plus 64.9 0.030. Right, so I'm dividing, that's what happens when you divide the weight by the cosine 40. Let me just see, I want to see something on the significant figures. Cosine 40. Yeah, that's weird. I don't know why I went that far. All right. Now, you could also rewrite this as TCB, right, in terms of TCA. So we can write it in either format, 79307 TCA minus 50.780. And why are we doing this? Well, we'll get back to this in a bit, but we're going to look at the differences between these two, because we're looking for a range. So we need to have equations that give us the tensions with respect to one another. And then we're going to hopefully get the velocity in here as well. So let's just look at what we got, because we want to be able to look at the equations and see one of these tensions is going to be limiting, right? When one is 0, the other one's going to be positive. So we want them to remain taut, right? So our minimum tension is 0. Our maximum tension is going to be 116 newtons. So we want to be able to see this in both tensions, right? We want to be able to write it both ways. All right, so let's look at the sum of the forces in the normal direction, which is now, let's see, basically the x direction. I'm going to use this as normal. Let's write this out. M-A-N equals. All right, so I'm going to write this x direction as positive this way, but notice our components are all negative. So let's write these out. I just write n is negative x direction, right? This is for direction. Just a little side note. Am I going to have room? That's the question. All right, so we've got TCA on top here, and the x component is negative, and it's a sine 40. And then we've got TCB, which has a negative component again, and that's going to be sine 15. The weight does not have an x component or a normal component, but we do have equal to mass times normal acceleration. So I'm just going to write in here, notice the direction of this, right? This is the negative m, and the normal acceleration is v squared over rho. And we're given information for both the radius, 0.9 meters, and v is what we want, right? We want to find v. All right, so we can rearrange this. I mean, you can see all the negatives can switch to positives. Let's see, v squared equals, let me just make a note here. Variable of interest. All right, that's what we're trying to find. So v squared equals 0.0. Oh, you know what? I was going to do I'm going to write the intermediate equation. It's 0.9 over 5 for the ratios, right? Rho is 0.9. And the mass is 5 kilograms. Sorry, this is 0.9 over 5 times the quantity TCA sine 40 plus TCB sine 15. And this gives us an equation for V squared equal to 0.0, or no, geez. I always do this with my zeros. 0.115702 TCA plus, this is 0.046587 TCB. These are the tensions right here. I don't know why I carried so many decimals. Usually I'll try to find a place to round that makes sense. Like, well, probably this, I didn't feel like rounding to 8. So I just went one more decimal point further. Again, you don't have to carry, if you carry like 4 digits, it's probably fine. So now we have 3 equations, right? To look at, and I'm just going to number them because they're technically not, we're not going to solve them. So we want TAC and TCB to be less than or equal to 116 newtons, right? So this is a little less straightforward than just solving something. So I'm going to say, okay, I'm going to take, let's set TCB equal to 116 newtons in equation 1, right? So again, I'm not simultaneously solving these things. I've just numbered them to reference them here. So I'm going to set TCB equal to 116 newtons in equation 1. So this gives us TCA equals 210.3 newtons. So this right here is not okay, right? Not okay. So all I'm looking here, this is why I wrote them out like this. I'm looking for if one of these is whatever, right? What is the tension of the other one? And these are the limiting cases. TCB is 116 newtons. That would be the maximum tension allowed in either of those strands, right? In fact, we didn't actually have to do any of the velocity stuff here. I just wanted to get all the equations out. But to do this analysis, you're just looking at these 2 equations. So now we're going to set TCA equal to 116 newtons in equation 2. And this gives us a TCB equal to 41.22 newtons. And this is okay, right? Less than 116 newtons. So this tells us that TCA is the limiting tension for the upper, the upper limit, 116. So TCB will never go to 116 newtons. It's going to go to 41.22 newtons, assuming you reach a maximum. This is the limit, 116 newtons. So TCA limits us from basically our highest velocity, right? So let's look at this. Let's put this in here. So V is basically the square root now of these 2, of this equation with these 2 values in it, right? This is our upper case limit. This is our maximum speed. So we're going to put these numbers in, and I'm going to have 0.115702 times TCA is 116. And then we've got plus let's see, TCB. Remember, I'm using the TCB that corresponds to that value of TCA. Oh, I put the coefficient in first. 0.046587, 41.22 newtons. I'll draw an arrow. This gives us a velocity of 3.92 meters per second. This is the maximum velocity or maximum speed, right? Because this speed gives us a tension of 116 newtons in CA, right? We're just sort of working backwards here. So now the minimum tension is 0, right? So let's look at these equations. Oh, I can fit them all. Sorry, I'm not looking at my screen here. So if TCB equals 0, right? So TCB, let's plug that in over here. If TCB is 0, right? TCA equals 64.03 newtons. Right, this is from, make a little note here, from equation 1. And you can see here, right, if you put in a tension of 0 for CA, right, so let's just write that. If TCA equals 0, TCB equals what? Negative 50.78 newtons, right? This is less than 0. So this would be no longer taut, right? TCB would be, now this doesn't mean you actually get a negative tension. This is just, this is not realistic answer. This is, it just tells you it's less than 0, right? So let me just make a note here. Not actually, negative 51 newtons, right? It's not actually negative 51 newtons. Like you're not going to be compressing your your wire. The wire is just going to be, it's just showing you mathematically it's less than 0. So you obviously have to, as an engineer, you have to recognize, oh yeah, well, the tension's negative. It just means it's less than 0. It's not a realistic scenario. You know, it's going to be, it's not going to be taut anymore. All right, so V min, let's write the min this time. In this case, TCB is 0, right? Which one was that? That was over here. So we're going to have 64.03 times this coefficient. So 0.115702 times the 64.03. And what does this give us? 2.72 meters per second. And this is our min. I'm going to fit this all on one page, people. So let's just write this down here. 0 is less than or equal to tension CA and tension CB. And that's also less than or equal to 116 newtons, right? You've got 2.72 meters per second is less than or equal to the speed, which is less than or equal to 3.92 meters per second. Let me box this in so it separates it from the rest of the mess here. All right, so this was not actually that complicated. This was just a matter of setting up the equations and then examining them. So that's why I set this up here both ways. This is technically not going to be solvable, right? Like it's not two equations, two unknowns. You're going to wind up with just you're not going to wind up with an answer here because they're coming from one equation. But what this does is it allows you to see what's the tension of one with respect to the tension of the other. And we just went through and we said we want no more than 116 newtons and no less than 0 newtons. And we figured out what the limiting tensions were, and then from there we got the velocities or the speeds. Yeah. So any questions about this particular problem? All right. Since you're all here, before we'll see if Blackboard is. If you go into learning modules, this is just what I wanted to show you here. I put in another. We had this in statics last semester, a supplemental information folder. I put in some information about I thought you might get a kick out of this. I wasn't sure. I'm like, should I put it in dynamics or mechanics and materials? I thought, you know what, this is more, well, it involves both, but I put it in dynamics. I just put in the videos. This is the video of, you probably heard the Perseverance, the Mars mission, the Perseverance rover landed. This links to an animation video showing how it did that. And I mean, if you just think about the amount of, time and effort and the number of technicians and engineers and scientists that work on this thing, and they landed successfully. But imagine you were at NASA and you've been working for years on something like this and it crashes, right? You're like, oh my God, all that work for nothing. But it landed. And then one thing of particular interest is this, the Mars helicopter. So this is a Veritasium video. They go through, he visited the site in, 2019, and he got a look at the helicopter. Well, at least a mock-up of it. The actual helicopter is like in a clean room that they go into. But the challenges of building this thing to keep it both lightweight and also to work in the environment it's got to work in. There was a lot of challenges to that, and to make it fly, right? And the testing's kind of cool too. He shows how they tested it in a large, NASA's got a huge vacuum chamber on Earth, so they can drop they can put whatever air pressure they want. But it's apparently equivalent to trying to fly a helicopter at like 100,000 feet on Earth, which is crazy because I think the maximum ceiling is like 40,000 from the numbers that they gave. And plus the gravity is different. So to test it on Earth, they had to sort of counterweight the helicopter to make it feel like it was in lighter gravity. So it's really cool. And they'll talk about terms in there that you should understand as they talk about torque. They talk about, I don't remember, the tip velocity of the blade, right? They don't want that to exceed sonic velocity. So some really cool video in there. I mean, it's 16 minutes. I know it's longer than your typical YouTube. I tell you, these days, if the video is longer than like 2 minutes, it's like, oh my God, this is gonna be forever. With all the short video clips that people post online. And then IEEE has an article about the helicopter. So this goes into more. This is just an article, and it talks specifically, and it's probably geared. Well, I didn't read the whole article because I don't know, something came up halfway through it, but I linked it, and I thought you might you might find it interesting there. So as we go, if something comes up or I see something in the news, I'll stick it in supplemental information. But I really got a kick out of I was baking banana bread the other day and watching it. My son and I were watching it on TV. I was like, oh, this is I haven't actually seen a NASA footage in a while, because it takes some time to sit down and just watch the mission, right? And You know, even watching Musk's rockets go off, it's like, okay, well, you know, gotta listen to these people talk, and you gotta wait, and then there's a delay, and this and that, and you're like, I can't plan my day around this. Okay, so back to the slides. that was the problem. But I mean, you know, dynamics, understanding dynamics is critical for any type of aerospace career. Everything's moving, right? A lot of things moving, and you know, you got to worry about all that stuff, friction. I mean, it's incredible, right? The you know, Mars has an atmosphere, but it's a lot less dense than ours. But you know, they talked about also, you know, we don't know what the particulates are like, right? Is it, how abrasive is it going to be to run these blades at, like, I think it's like 29,000 RPMs. It's crazy. But yeah, it's cool stuff. Okay, let's see. What did I have here? Do I have the solutions? Which slideshow is this? All right, I'm going to put up a. Oh, okay. This is for you to do on your own here. Let's just. A car is driving from A to D on a curved path shown. The driver is doing the following at each point. At A, going at a constant speed. B, stepping on the accelerator. C, stepping on the brake, and D, stepping on the accelerator. Now, what I want you to do is, just draw an approximate, or maybe just sketch this out on a piece of paper, and draw an approximate direction of the car's acceleration. Remember now, right? Normal acceleration and tangential acceleration. Make sure you draw the resultant of the acceleration, right? We're looking for the resultant, not the components. I mean, you can sketch out the components and then, you know, help yourself visualize where the resultant's going to be. So let's just take a minute to do this. What time is it? 9:35. All right, it's been about a minute. All right, I put these in here, or maybe they were in here. I don't remember. Point A, right? You're going at a constant speed. So in this case, the acceleration is only going to be, there's only going to be a normal component, right? Pointed in towards the center of the radius of curvature of that curve at that instant, right? So keep in mind, you can have a curve that is not circular, right? It's not perfectly circle, but the normal component of acceleration is pointing towards the instantaneous circular center of that point, right? So if there was a circle with that, you know, that particular instantaneous arc, it would point towards that center. And obviously, you don't need to know this for the approximation. B, stepping on the accelerator, right? It's in a straightaway. I think this was fairly straightforward. All right, I'm just gonna laugh at my own jokes. And then C, stepping on the brake. So what do you got going on here? Well, we definitely have a normal component because it's going around a curve, right? Due to the fact that it's going around a curve. And then we've got a backwards component for the acceleration because we're stepping on the brake. right? Because we're slowing down. So this makes sense. The arrow is going to be in somewhere in between. And I mean, you could draw it straight across. It really doesn't, you don't know the magnitude of any of these. And then D, you're stepping on the accelerator as you're going around a curve. So now you've got your normal component this way. You're accelerating instantaneously in this tangential direction. So your resultant is somewhere in between. All right, any questions about these? I think this was, again, fairly, and if you don't get it at first, you're like, oh, once you see the answer, it's like, oh yeah, I see what happened. All right, so let's talk about radial and transverse coordinates. I think this is the shortest section because everything is basically the same except for we just see the equations, right? And you would encounter this in a lot of different scenarios where you're just, you're spinning something, right? Or something's rotating about a point. So, hydraulic actuators, robotic arms, right? The centrifuge down here. And this is radial and transverse coordinates. So this is just showing the vectors down here, the sum of the forces in the R direction, right? This is some of the forces. This is the kinetic diagram. This force P, this point P is, it's got a force acting radially outwards, right? And that is this MAR. And then MA theta and some of the forces in theta are, tangential or perpendicular to this radial line. Anyway, you can write the coordinate, or you can write the equations in polar coordinates for radial acceleration and theta acceleration, right? Remember in the last example, we said, okay, there's no theta acceleration. We're just going to look at this in the XY, plane. So this is what it looks like, right? It's the mass times the second derivative of R minus R times the second derivative of theta squared, or first derivative of theta squared. And then we've got R times the second derivative of theta. This is for the theta component of acceleration, plus 2R, or derivative of R, and times theta, derivative of theta with respect to time. So this is, again, like I said, the shortest section. There's one slide here, and then we're going to do a sample problem. Is this one that I have? Oh, no, I don't have this. And all right, we're going to just walk through this. So this is a common device used in textbooks. A block of mass M can slide freely on this frictionless arm. So again, starting off just to keep it simple, right? What are the concepts that we're looking at? Let's ignore friction for now. I'm so tired this week. The arm is rotating in the horizontal plane, right, at a constant rate, theta naught. Here it is. Theta naught dot. It rhymes. Theta dot naught or theta naught dot. All right, knowing that B is released at a distance R naught. So this, it's not shown, but it's at a different radius, right? B is released at a distance R naught from the origin. Expressed as a function of R, the component VR of the velocity of B along this arm, right, OA, and then the magnitude of the horizontal force exerted on B by the arm OA. So there is a horizontal force exerted on B by the arm. So we're gonna write this out in radial and transverse equations. You're going to see you basically have to integrate the radial equation to get the radial velocity, right? Because if we go back for a minute here, in the radial, right, we've got a second derivative here. Then we can substitute what we know into the transverse equation and find the force on the block. Oop, whoa, Oh, I hit the end button again. This never happens in class. Oh, where the heck was I? Oh, wait. Oh, it took me, when I hit escape, it took me back to where I started. All right, look at that. That's exciting. Let's start here. I don't know if it's the way my keyboard is positioned, or I should use the down arrows instead of the page down button. All right, I don't know what happened again. I thought I cleaned up this slide. I remember going through this slide, and I don't remember that hanging down there. All right. So these are they're just to remind you, right? These are the equations. The sum of the forces in the r direction is equal to MAR. The sum of the forces in theta are MA theta. Now let's draw well, first we should draw this, the free body diagram. The free body diagram looks like this, right? And remember, there's no friction. So the only force is a result of this arm, OA, applying a force to B, right? And then because it's frictionless, right, you're also able to slide in either direction. So you're going to have an acceleration in the theta direction and an acceleration in the r direction. So let's write this out. Notice here, they're integrating the radial equation. Excuse me. Let's just look at this identity here. The second derivative of position, right, is the first derivative of velocity. Right, this is all this is saying. So we write this out, dvr dt, right, is dvr dr times dr dt, right? This is just your position derivative. And you can pull out your VR and get VR dvr dr from the equation. Let's see. Oh, yeah, and then this is the theta component, right, down here. So now we're going to basically plug in that identity we just came up with up here, right? This is just equal to each other. This is an identity, right? This is from the accelerator. This is from the sum of the forces equals the kinetic equation. So now we've got an expression we can integrate. VR dvr equals r, theta dot squared dr. And you do the integration, and you're integrating from 0 to VR and R naught to R. Remember, you have an initial condition for R naught. Did they give you the number here? Oh, it's generic in this scenario. So we know, right? We know what R is, or we know what the initial radius is. We know the initial velocity is 0, and we're going to sum VR and sum R. Again, you get an expression for. Notice here, right? Theta dot this is the theta with respect to time. This is not with respect to R. So this is just, you just deal with it as a constant. Pull it out of the equation. And then you substitute the information right, to get the force on the block. So we've got the force here, right, is, let's see, 2m theta squared, and we've substituted in this expression, right? R squared minus R squared, R naught squared to the 1/2 for the force. Oops. Oh, right, there's no numbers given. So really there's no, you have these two expressions. You can figure out the speed, right? Oh my God, right. The component VR of the velocity of B along OA and the magnitude of the horizontal force, right? And the magnitude of the horizontal force is just going to be, you have to break down this force vector into components. So that's what we're doing down here. Let's see. Yeah, this is not the best sample problem, but it's what we can do in the time. And I'm going to actually do one on paper the next time. But the point here is that you need velocity in the computations, right? And for this system, this particular system, it's just much easier to use this coordinate system, right, with theta and r than it is to try to break things down into x and y. Let's say the collar accelerates relative to the rod. Yeah, it's all relative acceleration. Let's see. Yeah, so we'll do that. We'll start with this example next time. And this is one we'll actually work through. This is similar, right? Similar coordinate system. It's just a little more complicated in terms of, you know, this tension, extra tension on the drum. So this is not exactly, you know, it's not like friction, but it's it adds in another variable, right? This tension here. All right, I'll see the rest. I'll see all of you this afternoon in mechanics. And if there's any questions, I guess